We started with one proportion, we ran to two proportions. Rapidly, we sort of jumped to not two, but many proportions to let you know that we could use this chi-square test to many proportions. We can still do confidence interval for pairs of proportions if we want. I showed you that. I didn't exemplify it, but I showed you it's there. The last thing we need to do today, and the last thing methodologically wise in our course, is that not only could we have three different samples, right? Again, we're having this voting, polling, but it could also be investigations of risks of various kinds related to sickness, or as you've seen. Maybe we do sort of three different polls at three different times, so that is 3 C equal to 3, like I've just said. That's fine, but hey, now I'm going to be more detailed on the response. I also talked about the malformations. They could come in different types, right? Severe, not so severe, and not at all. And again, if we would be more intelligent, we could work with 2 candidates and potentially undecided people also. So there's a 3-group outcome here. And we might be interested in all different proportions, both who they really would like to vote for, and also the proportions of undecided. Many times the undecided ones finally make the important difference at the end. So, the null would be, are the votes equally distributed? That's a way to express it, right? That the 3 proportions, there are 3 proportions in a way, right? That add up to 1, if I take one sample at a time. You could call that a distribution if you want. 3 proportions adding up to 1. Are those 3 sets of 3 proportions, are those the same? That's one way of expressing a relevant null hypothesis here. Has it changed the way people distribute their votes in this case? Or, here is a similar table at first sight. It's also a 3-by-3 count table, frequency table, or contingency table. All 3 words for me means the same thing. This is slightly different. This could be, let's just say, a math test and Danish. Why not English test? So, you take one person, I test you on Danish. You're pretty good at Danish. No, but that's another study. So I take you in this study I'm talking about here. We'll talk tomorrow about the Danish thing. So we take you on the English. You're pretty suck at the... No, sorry. You, of course, are extremely good at the English. I test you on math. Whoa, you're good at that. That's why you're here. So you become good at English, good at math. So you're one of the 63 down here, right? And then you have 62 friends down there in the nice group, right? Then there were also 79 people that were good, sort of average on English and average on math. So it's just a single sample data, actually. It's not different groups. It's one group of data, one sample. But I measured 2 things on people. 2 category variables were measured on people. And I've categorized you into 3 categories on both variables, and I make the count data like that, right? Count table. Now, actually, I would have, let me just see, I would have to phrase, I could at least phrase the relevant hypothesis slightly different from before. And I could phrase it that, and the null here is expressing there is no dependence between your math skills and your English skills. The null is your math skills and English skills are independent. There's no relation. And the alternative is there is a relation, right? That could also be a way. And this way of talking about a 3-by-3 table comes from the fact that this 3-by-3 table occurred in a slightly different way than this 3-by-3 table. I mean, the sampling mechanism, if you want to use Mustad's words, behind is a bit different. Here I decided I have one sample, second sample, and a third sample, and then I count within each sample. So I decide the sum of these. I think actually that's to be seen on the numbers. I believe if we add them up, as far as I remember, am I not right that these are all exactly 200? Because I decided that, I made the experiment. I mean, I didn't, but someone did. Someone made this decision, whereas this data set is slightly different. I didn't decide exactly how many bad math persons should I have in my data set, or how many good ones. It just came out as a part of the outcome of the experiment. When I see the table, 3-by-3 numbers, in a way, if I don't know the story behind the table, this is a bit, now you're getting a bit worried, because here is a difficult thing. I need to know the story about the table. So if I just get a table of 3-by-3 numbers, it's not maybe good enough. I need really to think about what are these numbers? How did they appear to me? What was happening before? What was the process, the procedure, the sampling that made me to have these numbers? The good news is that even though there are different ways that such tables that could come out as a 3-by-3, or for that sake 2-by-2, or 2-by-12, or 5-by-12, or 1,000,000 by 1,000,000, could have any size. Even though the hypothesis, the null hypothesis, could be differently expressed, funny enough, it's the same hypothesis. It needs a bit of thinking, actually. But it is the same hypothesis, so I could potentially express the hypothesis different here. Now let me do it. I could say the English distribution among the bad math people is the same as the English distribution among the good math people, right? That's a different thing than the dependent thing. But really it's the same, actually. That's nice. You have to know that these tables come in different shapes and forms and backgrounds. And you may talk about these tables in different ways. But at the end of the day, there is only one test you can make, in a way. It's just the way you interpret it, or the words you put to it that might differ. Because the good news is, look at this, instead of the 2, I put the R. So instead of 2 rows, I have R rows, right? So I use exactly all the same things that I've just taught you. For the multiple proportions case, I use that I have many columns and I have many rows now, generally. And I just compute all the observed, all the observed I'm presented with, that's my data. I compute all the expected ones, R by C, and I put them into the chi-square statistics formula, comparing observed with expected. And I use a chi-square distribution with this degrees of freedom, because theory tells us that's the right one to use. Number of rows minus 1 times number of columns. See how nicely, if there are 2 rows, this number becomes number of columns minus 1. If there is 2 rows and 2 columns, that's where we exemplified it. It's 1 times 1, chi-square with 1 degree of freedom, as we saw in the example. Again, same rule of thumb. Be careful. And if we are going to be strict about it, don't use these methods. If just a single one of the expected numbers become less than 5, don't do it. That's the safe advice, right? Rules say all the EIJs. So all the 9 ones for those data should be large enough. Otherwise, it doesn't work. That takes me to the R part now of this whole proportions chi-square test business. We have some